So far, all artificial intelligence has been special purpose intelligence that just does one or a few things. Large language models can do many things, but they still aren't very good at many human tasks like planning or long form logical reasoning, let alone the various physical things that humans do, like walking or folding laundry. But there has long been an idea that there might be a possibility of artificial general intelligence along the lines of what human intelligence appears to be. This lecture is about general philosophical issues related to the concept of artificial general intelligence. Specifically, the main issues I will consider are these. Is general intelligence possible? Does the idea of general intelligence relate to consciousness, the idea of having feelings or experiences or what it's like? This idea of consciousness is often thought to be very important for a lot of moral and ethical questions, often using the term sentience instead of consciousness. Finally, how does intelligence relate to embodiment? This might not initially seem to be an important question, but it may be related to the question of why the capacities of artificial intelligence have often been so different from those of humans. There are, of course, many more philosophical questions related to artificial intelligence, and even to the concept of general intelligence. And there's far more philosophical debate about all of these questions than I'll have time to cover here. This is just an introduction. Now, one reason why I think that many of these questions are particularly interesting is because so much traditional thinking about intelligence ties it to things like an immaterial soul that, according to many traditional viewpoints, is only temporarily attached to the body and survives after death. Things like emotion or feeling have sometimes been thought to be bodily features that are thus separate from truly mental features like intelligence. Though, of course, there are other religious traditions that have thought of the soul as the seat of consciousness and feeling, as well as thinking. But I'll suggest that a lot of current thinking might contradict this sort of general idea. Okay, so let's start with this question. Is general intelligence possible? I like the general definition of intelligence, according to which it's the ability to take in and process information, learn from it, and use it to make some sort of progress towards a goal. This sort of definition has the advantage or disadvantage of counting nearly all living beings as having some amount of intelligence and counting lots of very simple, even decades-old computer programs, like a restaurant reservation system that stores and uses information about which slots are occupied to help guests make reservations, or an expert system where the most experienced doctors in a hospital have all collated the questions that they think are most valuable into a system that even a junior doctor can use to determine the best course of treatment for a blood infection. However, beyond these general things that fit the basic definition, humans have long been interested in a deeper kind of intelligence, like the one that we think of ourselves as having, that allows us to think about many different kinds of problems, adapt to new situations, and have feelings and opinions of our own. One of the earliest projects to build a machine that could do intellectual work of any sort was the analytical engine. In the early 1820s, the British inventor Charles Babbage had traveled to France, and among the things he saw there was a jacquard loom that was using punched cards to weave complex patterns into fabric. He realized that he could use the same principle to design a machine that could use those punched cards to do mathematical calculations. After working on the first plan, the difference engine, for several years, in 1837 he planned a new machine called the analytical engine, which would be able to do a much wider variety of calculations and could in fact be programmed to do new calculations. At some of the events that he held to discuss his project, he had met a young woman named Ada Lovelace, who was a noblewoman by birth. She was the daughter of the poet Lord Byron, who had left her mother when she was a child, and she was the Countess of Lovelace through her husband. Babbage realized that Lovelace was one of the few people who understood the full significance of the project that he was working on, if he'd ever be able to complete it. And so over the next several years, the two of them worked collaboratively on this project, discussing how it would have to work, how you would design the machine, how you would build it, how you would give it instructions. And during this process, Babbage gave lectures on this in France and various other countries. And other European mathematicians and philosophers started discussing the idea as well. In 1843, Ada Lovelace translated one of the articles about this machine from Italian to English, and she added several major notes of her own to this translation. In one of the notes, she observed, "There's nothing really special about numbers. Just as the punch cards of the Jacquard loom could represent colored fabric, the punch card of the analytical engine could represent numbers, but could also represent anything else, like musical notes or words, so that, as she suggests, the analytical engine might be used to compose elaborate and scientific pieces of music, or anything else that you wanted to do." Babbage himself never talked about this possibility, but Lovelace did. Now, one other point that she mentions is in the last note, which has been the focus of most discussion of her work. In this note, she showed precisely how you would have to punch the cards to get the machine to calculate the Bernoulli numbers, which are an important mathematical sequence. And so this is often said to be the very first computer program, and she is often said to be the first computer programmer, though there is some dispute among historians about whether some of the instructions that Babbage gave in his work might also be thought of as computer programs. But more relevantly for our purposes, she made this observation. The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths. So although she saw the potential for the use of this machine for any number of intelligent tasks, she didn't think that the machine would really be thinking or coming up with anything new. It would all be the programmer. At any rate, Babbage's funding ran out before he was able to actually build this machine, so the world never really got a sense of the full implications of these ideas of Babbage and Lovelace until decades later, after many more developments in mathematics and philosophy. In the early 20th century, various mathematicians had been trying to define what a calculation is or what an algorithm is in order to figure out which mathematical problems could or couldn't be solved. And in 1936, as a graduate student, Alan Turing came up with a particular model that could clearly be implemented as a punch card machine like Babbage's. And importantly, in this 1936 paper, he showed that all of the different mathematical models of calculation or algorithm that anyone had proposed were actually equivalent. Anything that any one of them could do, all the others could do as well. And this is now said to be the phenomenon of universality. There is a single machine such that you can give it instructions and it can solve any problem that can be solved by any computational process. Turing's doctoral advisor, Alonzo Church, had come up with one of these earlier models, and the two of them together conjectured this is more than just a mathematical phenomenon. In fact, as they thought, anything that any physical system could do should be computable in precisely this sense by one of these machines, so that one of Turing's machines could do anything that any physical system, including a human, could do. During the Second World War, Turing started building some of these machines to help the British government break German codes. And after the war, he started working on broader development of these machines at the University of Manchester. In his 1950 paper, Computing Machinery and Intelligence, published just 2 years before his death, Turing doesn't spend much time talking about the concept of intelligence itself, despite that being in the title of the paper. Instead, he addresses the question, can machines think? On the basis of the Church-Turing thesis, Turing was convinced that since physical human beings can think, computers must be able to as well. And in his paper, he spends quite a while replying to Ada Lovelace's objection. He argues that although it's true that a machine can only do what its instructions say, those instructions can give rise to extremely complex behavior that the person who came up with the instructions wouldn't have anticipated. And he was basing this on actual experience with computers that he had been building and working on in the 1940s, whereas Lovelace had been working with the general idea of a computer, and she could see how it would have to work, but didn't really experience computers doing surprising things. Those of us today who have been able to see much more complex computer programs are even more struck by the point that Turing makes. He suggests in his paper that humans might ourselves be thought of as physical machines that operate according to the laws of physics and the structure of our brains, which is equivalent to some sort of extremely complex computer program. He thinks if someone were to really know the full program of a human being and have the computational power to run it, maybe they would be able to predict everything that a person would do, and they would see the person as just a mere machine. But because none of us know the specific program that corresponds to another person, we see each other as making surprises all the time. Just as Turing saw computers doing surprising things all the time, because even though he knew what program he was writing, he didn't always know what that program would do when you applied it to certain tasks, though he could have figured it out if he had spent ages working it out. Lovelace is right that a computer can't do anything other than what it's programmed to do, but Turing thinks that this is just the same as what's going on with what we call thinking in humans. Now, his paper is most famous for a test that he proposes for thinking. He says, just as with another person, we can never get inside their head to know whether or not they're thinking or what it is like for them to think. The only thing that makes us say that another person is thinking is the fact that we can have conversations with them, feel like it was a productive and interesting conversation, and be interested enough in what they have to say that we keep coming back to have more conversations with them. At one point in his paper, on the basis of his guesses about how complex the human brain is and how fast computing power will advance, he predicts that by the year 2000, computers will be at the stage where a person having a 5-minute conversation by a chat terminal with a computer would only have a 70% chance of being able to tell whether they were having a conversation with a person or with a computer. Now, some people in recent years have taken this simple definition, a 5-minute conversation, 70% chance of telling the difference, as the definition of the Turing test. But Turing himself thought that it was a longer interaction. It was the possibility of really having an extended friendship with the computer that matters. Nevertheless, because Turing's machines are universal for computation, and because he thought the physical world as a whole was computable, he was convinced that computers would someday do it, though by the year 2000, he only predicted this smaller thing. Over the next several decades, though, various philosophers argued back against Turing's idea. One of the most famous objections to Turing's idea is due to the philosopher John Searle. In a paper in 1980, his main objection was that Turing defines thinking just in terms of having intelligent interactions with inputs and outputs. And so Searle asks us to consider a computer that could pass the Turing test, answering conversations in Chinese. Now, he notes that any instructions that a computer could follow, a human could too, though it might be a lot slower. So Searle tells us to imagine a man in a room with all the instructions for this computer program who receives sheets of paper or input on a screen with Chinese writing on it. And he looks up these symbols in his book and follows the instructions in the book, does various processing, and eventually writes down some new symbols and passes them out. From the outside, it looks like the person is having a meaningful conversation. But Searle notes the person who follows these rules could do all this without actually understanding Chinese themselves. And thus he claims that being able to have these sorts of interactions isn't enough for really thinking and really being the kind of thing that understands Chinese or any other language. He claims the computation is not enough for sentience or true experiencing of the conversation or really any other sensation at all. Some people have been convinced by Searle's dramatization of the idea, but a lot of philosophers object. They point out that any computer program that passed the Turing test would have to be extremely complex, and the instructions wouldn't be able to fit in a single book like Searle was imagining. For instance, a single person in a room couldn't have the instructions and carry them out. ChatGPT requires billions of neurons implementing trillions of instructions that would take more than the entire Library of Congress to describe. And so the system's response to Searle's argument is to note that it would really have to be an army of people who are dealing with massive set of instructions like this in order to implement the Turing test. And in this case, we might say no individual human who is part of this understands Chinese, but perhaps the system as a whole does. and this might be thought to be analogous to what goes on inside a human head. No neuron in any human's head understands Chinese, even though there are people whose brains are made out of neurons, and those people understand Chinese. Now, one thing that's important to note is Turing doesn't actually ever make any claim about the machine understanding anything. He just claims that all we mean by intelligence or thinking is contained in the interactions, what the system does, because that's all we can tell about another person. Whether or not there is some further concept of experience or consciousness going on in another person's head or in a computer is a thing that Turing never speculates about, and he doesn't think we can know that about anyone else, let alone a machine. And so he thinks it doesn't matter. This idea that a system that is behaviorally like a human would be conscious like a human is said to be the strong AI hypothesis. And this is what John Searle was arguing against. Now, the philosopher Dave Chalmers makes a similar point. He distinguishes this idea that he calls the hard problem of consciousness, which is explaining whether and how a physical system of any sort, like a human, can give rise to consciousness, and whether Turing's account of intelligence or thinking is enough, or whether it's something else. And he contrasts this with what he calls the easy problem of consciousness, which of course is not at all easy, but has been the product of decades and decades of work by cognitive scientists and neuroscientists and psychologists and artificial intelligence researchers and philosophers who have been trying to figure out how is it that the human body is able to do the things that from the outside seem like consciousness. The strong AI hypothesis says there's no distinction between the easy problem of consciousness and the hard problem. Once you've solved the easy problem, you've solved the hard problem. And Chalmers is trying to object to this. He says that the hard problem is truly difficult in another way, and so he wants to reject the strong AI hypothesis, as Searle does. Now, another set of critiques arose in the early 1960s and 70s when much of the early work in AI was being done. There was a series of critiques by the philosopher Hubert Dreyfus, and in some ways, his arguments were focused on the opposite set of issues as Searle's. Dreyfus argued that the symbolic AI paradigm of the time, particularly expert systems, seemed to be making a series of assumptions, a biological assumption, a psychological assumption, an epistemological assumption, and an ontological assumption. They assumed that all of intelligence could be understood in terms of knowledge, that all knowledge could be put into symbolic form, that these symbols could be manipulated by a symbolic system in the same way that a human mind works. But he noted that much of human intelligence involves intuition and actions and skills that can't be put into words. You might know how to ride a bike or know how to interact with customers to get good tips without necessarily being able to put this knowledge into words. While Searle was trying to argue that even a perfect AI duplicate wouldn't be consciousness or have experiences, Dreyfus was trying to argue a perfect AI duplicate wouldn't be possible. Now, many AI researchers have actually agreed with Dreyfus's critiques, but suggested that there are two important pathways around it. One is that modern AI systems are based on neural nets, which don't involve explicit knowledge manipulation or symbols at all. Their ability to learn from experience has many similarities to the kind of human skill or know-how or intuition that Dreyfus emphasized. Another aspect of Dreyfus's critique is that much human skill depends not just on our brain, but on our body. It's obvious, in some sense, that knowing how to ride a bike depends in some way on being at home in your body. The muscle movements that help me balance on a bicycle will be different from the ones that work for you if you're either bigger or smaller or have subtly different knees or feet. If these AI researchers are right and Dreyfus is right, then progress in robotics will likely have to be an important contributor to truly general AI, even beyond the symbolic and neural paradigms that have both contributed to progress so far. Now, there are some cognitive scientists that have argued that our bodies are essential even for more apparently abstract reasoning. George Lakoff and Rafael Nunez have even argued that embodiment is essential to our understanding of mathematics. At any rate, these critiques about embodiment help make sense of an important observation over decades of work in artificial intelligence, often attributed to the roboticist Hans Moravec. Many of the things that are easy for humans are very hard for computers, and many of the things that are very easy for computers are hard for humans. Computers have been better than humans at arithmetic almost from the beginning, even in the days of Babbage. And they've been beating humans at things that humans find difficult, like chess, for decades. But it wasn't until after 2010 that computers were able to do very simple physical tasks for a human, like telling a dog from a cat or walking on 2 feet, let alone such difficult tasks as folding laundry. As of August 2024, computers are now regularly passing simple versions of the Turing test, though they're not yet providing the long-term interesting interactions that Turing envisioned for true general intelligence. It remains to be seen how much the neural paradigm and embodiment might be necessary or sufficient for passing this idea of general artificial intelligence, or whether further developments are needed. We may never be able to address the philosophical questions raised by Searle and Chalmers about whether a machine that has general intelligence would actually be conscious and have experiences and desires, let alone rights and moral interests. But this has been a long-term philosophical dispute, even about other humans. It's only in recent centuries that we finally came to the understanding that all humans are conscious and have rights and feelings. And people still argue about animals. And general artificial intelligence will produce a new version of many of these same philosophical questions.